This example comes out of section 6.2, sum difference double angle identity. In this question we're asked to do something a little bit different. We're asked to write as a single trig expression this weird looking one, sine of 37 degrees times cos of 23 degrees minus cos of 37 sine of 23. Hopefully you recognize it as the structure of it looks a lot like the difference identity for sine. I've got sine cos minus cos sine. Sine A minus B, if you recall, and you can look right at your formula sheet right now, is sine A cos B minus cos A sine B. So for this particular question, A and B are 37 and 23, so I could say this is sine of 37 minus 23 degrees, which would be sine of 14 degrees. That would be writing it as a single trig expression, so I don't need to evaluate what sine of 14 is. I'm done with that one. Second example looks a lot different, but is actually very similar. We have cos squared pi over 4 minus sine squared pi over 4. Now realistically, pi over 4 is a number we know. We could figure out what these equal, and you'd actually find out it equals 0. But looking at the structure of it, it does look like the double angle identity for cos, because cos 2a equals cos squared a minus sine squared a. So what does that mean? It means instead of a, I've got a pi over 4, so this would be cos of 2 times pi over 4. Now, 2 pi over 4 is just pi over 2, so I've got cosine of pi over 2. Written as a single trig expression, that's what they're looking for. Now, it's also true that cosine pi over 2 is 0, and that confirms or verifies what we just said a second ago, that cos squared pi over 4 minus sine squared pi over 4 would also equal 0.